Hey, welcome back to Calculus. In section 3.11, we're going to take a brief look at some functions called the hyperbolic functions. So you can see the objective there. I want to just tell you about their definitions, look at some of their properties, the usual stuff, domains, ranges, stuff like that. The calculus of them, of course, know their derivatives. You can think of this, it's almost kind of a chance to take a breather. We're not going to really develop a whole bunch of new material. And these functions, you'll see they don't really need to be called these things, but there's just a lot of convenient properties if you think of them this way. So I want you to have these tools in your tool belt. They're important functions in science. I want to kind of give you a glimpse of that. And if you're going to take further calculus courses in Calc 2 in particular, some integration techniques become available if you have these functions under your belt. So it's an important thing for me to kind of introduce to you. Maybe you've already seen them, but let me just tell you a little bit about these hyperbolic trig functions. All right, so I'm going to treat this kind of briefly, not do a lot of computations in this. I'll do a little bit, but I try to make it brief. So this is just from the text that these functions, e to the x, e to the minus x, those exponential functions, you've seen them, they come up in growth and decay problems, all kinds of problems in mathematics and physics, biology, all sciences. So in particular, combinations of them come up a lot. So these combinations get these special names, these hyperbolic functions. So you're looking at the definitions of them. There's 6 of them. And sometimes people call them the hyperbolic trig functions, hyperbolic trigonometric functions, because their names go like that. These things are called, you read them out loud. This is the hyperbolic sine. Oops, sorry about that. I thought I had to highlight a hyperbolic sine function. It's defined like that. It's e to the x. I'm not going to say them all out loud. It's e to the x minus e to the minus x over 2. There, I said 1. Hyperbolic sine. You can also, people say sinh of x is how you kind of pronounce that thing. Sinh of x. This one, the hyperbolic cosine, cosh of x. You just kind of read it, cosh. Tanh, that's how people say it. The hyperbolic tangent. And the hyperbolic tangent, just like its trigonometric cousin, it's the hyperbolic sine over the hyperbolic cosine. Yeah. So if your trigonometry is sharp, you're kind of looking at these things going, okay, yeah, it's sort of funny to pronounce them. Cosech, sech, cotanch, just the analogs of the trig functions. So the 2 fundamental ones are these guys over here, right? Those are the ones that have the exponential function definitions. And the rest of it is just like, and by analogy, there are these 6 hyperbolic functions. And I wish, I'm not going to build it into a video, of course, but it's a beautiful, these things have beautiful connections to trigonometry, and the mathematics is just so deep and lovely. I'll show you just a teeny taste of it. It's a shame, but again, my purpose is I want you to have some exposure to these things so that you can use them as tools. Okay, so I'm going to keep moving. Know some properties of them. I didn't bring all 6 here. You can use Desmos to look at the other 3, but I've got hyperbolic sine, cosine, and tangent here, left to right. And I kind of wrote them out a little bigger because it's hard to see right under those where it says figure, the definitions, it gets a little bit cut off. But in all 3 graphs, the red curve is the graph of the hyperbolic trigonometric function. Yeah, so the author's showing us, you can see it, but let's just walk through it. The author's showing us like, oh, well, here's the, e to the x over 2, and here's the e to the minus x over 2. And if you add those together, you get the hyperbolic sine function. Or sorry, you subtract. Or you add those 2 things. He built the minus sign into it, yeah. So same over here. Here's the pieces, you add them together, you get the hyperbolic cosine. So you can just sort of put this stuff in your pocket, that they're all 3 defined for all real numbers. Every one of the hyperbolic function is defined for all real numbers. That follows because the exponential functions are, yeah, and in particular because the hyperbolic cosine is never 0. Hyperbolic tangent's defined for all numbers. They don't all have the same range. The sine does. I'm just doing this from the graph. If I look at that graph of the hyperbolic sine, I can see that every point on the y-axis is going to be an output value. The hyperbolic cosine, and that's not true. The hyperbolic cosine of anything is never less than 1. Again, that's from the graph. There's no y value less than or equal to 1 on that graph, but every y value bigger than 1 has a point on it. And likewise, I won't belabor it, for the tangent, it's between -1 and 1. It has horizontal asymptotes, hyperbolic tangent, excuse me. So some good properties to know. Okay, moving on here. This is just to kind of keep you hopefully interested that these things are all over the place in applications. Here's some famous ones that if you take a cord, a cable, something that's flexible, and you suspend it between two points that are of equal height and let it fall into that shape, like this over here in this picture, then it falls into the shape of the function that describes it is a hyperbolic cosine. These numbers C and A, they're parameters that depend on, how tall, how the poles are and how far apart it is, tension of the cable, and so on and so on. So the physics kind of bears out what these parameters should be. But a cable falls into the shape of a hyperbolic cosine. Those things are called catenary curves. So that's kind of a famous application of hyperbolic cosine functions. I think another kind of cool one is that the hyperbolic tangent function is related to the velocity of a wave moving through water. It depends on the wavelength of the wave and the depth of the water. And you can check out that picture. These are both from your text, so you can check them out there. That there's some constants in there again. But yeah, so this is just to kind of show you that, yeah, that these things kind of arise in physics. One of your homework problems, I'm going to have you think about this velocity function. Okay. Not making this computationally heavy. So here's a little tidbit that is, if you're wondering why are these things named in this trigonometric way? What's the deal with this association? Well, maybe you remember that in trigonometry, for a real number t, which you think of as an angle in trigonometry, I'm kind of looking at this picture on the left, that angle determines a point on the unit circle whose x-coordinates are cosine and sine. So if you like cosine and sine are these sort of things that come about from solutions of this equation, the equation of the circle, x squared plus y squared equals 1. Sort of a 30-second summary of trigonometry. That angle also, I'm not going to prove this right here, but it's kind of intriguing. It also happens to be 2 times the area of that sector. You just need to know the area of the sector of a circle. You take the, I'll write it here real quick if you want. The area of a sector of a circle is 1/2 the angle of the circle times the radius squared, which in this case would be 1 squared. All right, so the area of that sector is 1/2 that angle. Yeah, so twice that area is the angle. There you go. I did prove it. So why am I telling you all of this? Well, because over here on the right, I have kind of a related equation. X squared minus y squared is 1. Its graph isn't a circle, it's a hyperbola. Hyperbola has 2 branches, and in particular, I'm only interested in this right-hand branch of this hyperbola, because if you take a number, that number corresponds to a point on the hyperbola in a kind of similar way. T isn't an angle anymore, but this kind of hyperbolic shaded area there, twice it is equal to t. So if you take t to be twice that shaded area, then that ray, only one ray will have that property per t, and that determines your point on this hyperbola. So you can kind of associate these x and y coordinates to the hyperbolic cosine and the hyperbolic sine in the same way that you can cosine and sine in the trigonometric case. All right, so that's sort of the relationship between them, and that's why they're called this thing. And then in particular, they have these identities. You may have been looking at them while I've been talking about the pictures down here, but I'm not going to write proofs of these things in the video lecture. It'll be long. The proof of, I think, this main one, which follows from the kind of definition down here, if you believed me, is written out in your book. It's just an algebraic calculation. I'm going to ask you to think about some of these in the Tier 2 homework problems. All of these things are done just by calculating. They're important to know. I mean, again, you're just getting to know these functions. It's nice to know properties of these things because you're going to use them as tools. All right, I'm happy to help you or talk about calculating any one of them in an office hour, so feel free to drop on by. Let's do a little bit of calculus. I'm feeling a little guilty here, not doing anything. Let's compute the derivative of this hyperbolic sine. So how would we do it? Well, we're just going to convert back to what its definition is. The hyperbolic sine, by definition, is equal to that expression in exponentials. And if we're going to differentiate that, well, the 1/2 is a factor that just stays out in front. And so I'm just differentiating the numerator, and the derivative of e to the x is itself. And by the chain rule, the derivative of e to the minus x is minus e to the minus x. So we get 1/2. Change that arithmetic, and that's equal to the hyperbolic cosine. All right, so that's kind of cool. The derivative of hyperbolic sine is hyperbolic cosine. So that's the only one I'm going to do. I hope you'll do the others. It's good differentiation practice. The hyperbolic cosine, you'd have to differentiate the same way. You have to go back to definition and see what you get. And then, but the other ones, tangent, hyperbolic secant, blah, 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 you can just use the quotient rules. Well, with these, just like the trig case. All right, so here, well, we can gaze at them. You have the book, I have the book. I brought these. It's kind of a cool result. The one that we just computed together is right there. We just computed that this hyperbolic sine's derivative is cosine. So these are pleasantly familiar, but be careful with them. Look, the derivative of hyperbolic cosine isn't minus. Yeah, so you got to get kind of used to it. There's a lot of patterns. Look at it, it's amazing. Tanh, sech, those things kind of behave very, very much the same in the derivative sense. Yeah, it's intriguing. Ask me about it if you want to. We can have a conversation. Okay, but here let's just be practical. Let's compute here. I got a chain rule problem for you. Look, we know the derivative of hyperbolic cosine. It's written right up there, and we want to take the derivative of this combination, right? So what are we going to do? Well, the chain rule would say take the derivative of hyperbolic cosine. It's written up there that it's the sinh, and you got to evaluate it at the same place. And then I got to multiply by the derivative of that inside function. Looks like 2x plus 1. All right, so there's the derivative of hyperbolic cosine of x squared plus x plus 1, for example. So your homework and activity is going to be mainly stuff like that. Get you to think about domains and ranges, just checking to see there's nothing else down there. And then practicing some differentiation of these things. And then you're armed to use them. And again, they'll be particularly handy if you're going to take physics courses or calculus too. And in this course, I'll bring them into the example set so I can keep you fresh on their derivatives and their properties. All right, thanks for listening.